So here we are back for our second video of Chapter 2, Section 3. Here we are just going to focus on average atomic mass. I mentioned earlier this value we find on the periodic table is the average atomic mass. What does that mean? Well, this value represents a weighted average of all of the naturally occurring isotopes of that element. And by weighted average, we are taking into account two pieces of information: the relative abundance, or natural abundance, sometimes just abundance, and the mass of that particular isotope. So based on how often a particular isotope is present as compared to the other isotopes, and then the mass of that particular isotope, is how we are going to get this weighted average. So you can see an example here of boron that I have. Boron is composed of two isotopes. So boron 10, with a mass of 10.0129, has an abundance of 19.9%. That means that if I have an atom of boron, 19.9% of the time, I'm going to have boron 10, which means 5 protons and 5 neutrons. 80.1% of the time, I'm going to have boron 11 with 5 protons and 6 neutrons. I mentioned in the last video, we want to get in the habit of identifying specific isotopes. If all we have is the periodic table and the average atomic mass value, then we can round that and use that as the mass number. But I would much rather be speaking about individual isotopes. So let's see how we're going to do this work. What I'm going to do for every isotope I have, I'm going to take the relative abundance in decimal form and multiply it times the mass. Now, I would love to have this mass value because you can see the sig figs. If I don't have that, I could still just use the mass number used to identify the isotope. So using the atomic mass here, 10.0129, is going to end up giving me a much better value because of sig figs than being left with just using the mass number of 10. I'm going to do the same thing here for every isotope. In this case, there's only 2. And when I get those values, I'm going to get 1.99 here, round to 3 sig figs, and I'm going to get 8.82. When I've done that work, so now I've taken into account its abundance and its mass for that individual isotope, I'm then going to add those values up. So in this case, there's only 2 to add, but when I add these up, I get 10.81. And you see how close that is to the value listed on the periodic table, just a function of significant figures being the difference. So first we need to be able to do that work that I've shown here to calculate the average atomic mass, but we also need to be aware of what these values are telling us. If I were given a problem or a scenario with regards to the isotopes of boron here, but were not given these relative abundance values. So really all I know is that I have 2 isotopes of boron, boron 10, boron 11, and I can see the masses there. Really, I don't even need these masses. If I were to ask you which one of these isotopes would I expect to see more often you can answer that question based on the average atomic mass value. So since I have two isotopes here, boron 10, boron 11, and my average atomic mass value as listed on the periodic table is 10.81, that value is closer to 11 than it is 10. So I would guess here that boron 11 would be the isotope that occurs more often in nature as opposed to the boron 10. Often the isotopes that you'll find have really high percent abundance values. So you might have one isotope that's in the 90% and then other isotopes that are fractions of that. So it sometimes becomes quite clear that which of the isotopes happens more often and therefore would have a higher abundance. You may be wondering, how do we get these relative abundance percentages for the different isotopes? And we use an instrument called a mass spectrometer. Looks something like this. So the sample enters here and it's vaporized, and then the ions are accelerated, and we get the separation here of our different isotopes based on their relative abundance and the different isotopes listed. So we would be able to get some information that looks like this, and we can see the separation of the isotopes there. Okay, that's it for this video on average atomic mass, and this also wraps up our videos for section 3 of chapter 2.